Hi everyone, welcome to day 15 of Advent of Code. Today's challenge is called Warehouse Woes. So now we are back in our mini submarine, and every historian is driving their own submarine again. But now we see that there are some lantern fishes and they need help. And these lantern fishes have need a lot of food, so they have these robots which help them arrange and store food for in the future if they ever need it in the case of emergency or to eat. So they have this warehouse where they have all their food stored and the robot helps them. But something is wrong with the robot now because they can't control the robots anymore, and they are too scared to go close to it and then turn it off because the robot's movements are very unpredictable. So now we are given a map and a set of instructions for the robot. So based on these instructions, the robot will move, but there are some conditions. So this is our robot, this @ symbol. So if suppose the robot is here and the instruction is to move left, if there is an object here, the O's are objects and the hashes are the walls. If there's an object here, it'll push it to the next spot. And then if it has to go left again, it can still push it to the left. But if there is a wall, then it can't push it. And the robot is strong enough to be able to push like 10 objects next to it, as long as it's not being stopped by a wall. So this is an example given to us where initially the robot was here, then it's asked to move left. It can't move left, so it'll just stay there. Then it's asked to move, the instructions are to go up, then go up again, but it can't do anything because of the wall. Then the instruction is to go right, and you can see this is moving one bit, like it's moving the box to the right once. Then the instruction is to go right again, and both these boxes or the objects move to the right. But now if it's been asked to move right once more, it can't do anything because there's a wall here. And here there are 4 objects and it's asked to go down, but it still does push it and go down. But if it's asked to go down again, it can't. So that's how it goes, and finally we get this state where instructions are over and the robot stops here. So now finally what we have to do is we have to get the GPS coordinate of the box, and they have some scoring for it. So how we calculate that is from the top, how many ever positions it's below it, we have to multiply that with 100. So in this case the object is 1 from the top, so it's 100 multiplied with 1, and from the left, whatever position it is, we have to add that to this product. Okay, so good question. Let's see how we can solve it. Okay, so we've got our result here. So I'll explain the code quickly. What we're doing initially is, okay, so firstly we are inputting, like we have 3 inputs this time. I took advantage of the extra information they've given us and the extra samples they've given us. So this is our dummy input, and this is our dummy input 2, and then this is our actual input. So I'm importing all of them to test each one of them. And so first we are processing the input. Again, since it is split, 2 parts of the input exist. One is the direction in which the robot will move, and then there's the map. So first we are splitting the map and the instructions. In the map we are again splitting it by each new line character, and then splitting each character. And then in instructions we are replacing all the next line characters with nothing, and then splitting them because it's supposed to be one single string. So we're making it one dimensional array. Then we're returning this. Then we are finding the robot location because we need to know where the start point is. And in the map we are removing it and making it a dot because that's a possible movement place. So that if we have to move some boxes or something, then this will be a possible option. Then we are simulating the robot movement. We are going through each instruction. Then we are checking if the movement is possible in the map for the current robot location. I'm storing the robot location as a array of x and y, so that it doesn't change due to pass by reference. I'm duplicating it, and then I'm providing the direction to this method. If this returns that we can make a move, then we change the robot position to whatever the next position will be. This is another method. So then now check if movement is possible with taking the map, the robot location, and then the direction. We get in the next position, same as what we did before. And then for this next position, what is the object in that position? If it is a wall, or if it is a wall, then we will return false. If it is a free space, then we will return true because we know the robot can move there without having to do anything. Then if it is an object there in that place, then we will check if the object can move to the next spot. For that, again, it will check if the next spot has a wall or a free space. In that case, it's pretty straightforward. But if it's another wall, then it will again check, and it will keep checking till it finds either this or this. If it finds this, that means all of these objects can be pushed once, and then if it is possible, then it will push it. It will make the next space free, and it will push the object to the next position. So then the next one can push it to this, and so on. It will keep going on, and it will return that if movement is possible, then the robot can move to that free space. Finally, what get next position is doing is it's checking the different directions. Based on the direction that we have, it will change the current position to that. So we'll get a new position based on what the current position is. And if we're going up, we will reduce the I value by 1, and if we're going right, we will increase the j value by 1, and similarly for down and left. Finally, I made this method to visualize, which looks something like this. So before all the movement, it will look like this for the smallest input, and after it looks like this. And then get GPS coordinate values, they were telling us to see wherever the object is. If that object is like 1, 2, 3, 4 places from the left, we have to multiply it with 100. Sorry, if it is 4 places from the left, we just add it. But if it is 1 place from the top, or how many ever places from the top, we have to multiply that with 4 and add it to the j value. So for that, we are using this get coordinate values, where we are keeping track. We didn't have to, we could directly just make the sum of all the results, but just it's easier to check like this if we are getting the right values for each position. So debugging is easier, and so we're getting the right result for both the dummy inputs. So let's test it for the actual. Okay, a good number. Let's see if this works. Okay, now let's see if this answer works. Cool, simple enough. Now I'm scared for part 2. Okay, in this part, they have made the question a little tricky in the terms of how we're going to solve it now. So the map is the same, but there's another type of a warehouse where the robot is malfunctioning, and this map is exactly the same as what we had before, except everything has doubled in dimensions except for our robot. So if the wall was only singular before, now it's become a double wall. If there was a single spaced object before, now it's a double spaced object. So that's how it's become. And now because of this, there is a bit of a complexity. So suppose your robot is here and you push it, it still moves only one point at a time. So it can be in such a place where we have one box, two boxes, and then a single box. So now if it pushes it up, then all three boxes together will go up. So we have to keep track of that, and that's going to be sort of tricky. But anyway, so the calculation will be the same, and instead of looking for the O, we have to look for the left bracket. Okay, let's try to solve this. Oh my god. guys, we finally got the solution for this dummy input, and it was a lot of thinking to do, but I'm still not sure if it'll work for the actual, the alternate dummy input. So let's try that. I'll comment this one and this one. I think in the question they're talking about the scaled up version, which is, this was the smallest, this was the scaled up. So let's try it with this. I don't think we need to visualize at every step. I'll just see what the last one is. And the first one was I was using this to debug. There were a lot of bugs which I had to find and fix. Okay, see. Damn, great. Okay, it works. I just realized I haven't completed it by calculating the coordinate values, so I'll do that and get back. Okay, so calculated that as well. Now, not much, I can't say not much has changed. Actually, a lot has changed since we last met. So we were just splitting it, everything was fine till here is the same, but instead of directly returning the map as it was, we are now modifying the map. What modify map does is, if it is a robot, then it puts the position, inserts the @ and a space next to it, whereas if it is an object, then it makes it into this sort of object. And remember that this is happening in the single array location. So suppose it is 2 2, in that we are getting two characters in that place, so it's not proper. So what we do after doing this is, after adding a space next to the robot and two brackets in place of the object, and wherever there were anything else, it's being doubled, so the hashes and the dots are being doubled wherever it was. So after that, what we are doing is, we are joining the whole thing to make it one single string. After that, we are splitting it again to make it separate arrays, and it becomes something like this, where that simple map is now a little bit complex. So we modify map that way. The instructions remain the same. Find robot location also remains the same. Simulate robot movement, this method remains the same, but this is where the main mess up comes in. So I didn't need that variable that I had created, so I've cleared it up. So now we're checking if movement is possible. So if you notice, the scaling has always been done on the y-axis and not the x-axis. So if you're moving up or down, it's all good. I'm assuming that the x-axis is vertical and y-axis is horizontal. So if we move up and down, nothing, that is when things have become a little weird. If we move left and right, since everything is already scaled on the y-axis, so it doesn't matter. It's like you stretched an object out from left to right, so it doesn't make so much of a difference, because the scaling for the robot will not matter in that case. Because if it was a 1, if the dimensions of the robot is 1 1 and the dimensions of the object has become 1 2, so it can still travel in the horizontal direction the same way, but in the vertical direction it makes a difference, because this object is only touching one point of the robot. The robot is only touching one point of the object. So if you notice, if we are doing the same thing, next position object is a wall, or if it is a dot, then the cases are the same. But in case it's not that, and we are checking if it is an object, the left side or the right side, and if the direction is horizontal, then we are doing almost the same thing. But if the direction is vertical, we're checking the delta y, which means if it is the right side of the box, then take the left side as well, or if it is the left side, then take the right side as well. So find the corresponding position of that. Check if the movement is possible for both of it. Movement possible for the current side of the box we are touching and the corresponding side of the box which we are not touching. Both of them will move together since it's a single object. Only if both of the movements are possible, then we will move. Excuse the dogs. There are some dogs barking outside. I'm not sure if the mic will pick it up. But yeah, so then we are checking the next to the next position of we are checking the next to the next position as we did before, and also the corresponding next to the next position. We're using the delta y for that. Now this is where we do the whole movement if it is possible. That means both of the sides of the box can move. Then we are moving one side of the box first and then the second side of the box first to the new location, and then we are returning the value so that the robot can also move accordingly. So with that, we are getting this, and now the rest of it is pretty much the same. Here I've just added in visualize, I've added the robot location also to be shown. So now let's try it for the actual input. Okay, let's see if this works. Alright, so I think I messed up a small part of the logic in the last one, which now I fixed. So here we go. Let's copy this one and then check if this works. Oh, finally. So I was doing this thing very late at night, around 1:30 a.m. and then I had to wake up very early. So I tried to do this till 2:30 and then I had to give up for that moment because I had to wake up very early and it was important for me. So then I got some rest and I've come back now to do this. And it worked. So basically I needed some good rest before continuing to work on this. Anyway, that's cool. We considered some things and I forgot that I haven't explained the code yet. Should have done that first. So not sure what I explained in the last part, but process input is the same. Modify map. I think I explained modify map. Robot location simulate. Okay, yeah. The only thing I didn't explain was here we are checking if the current the position above the robot or below the robot, if that is movable, we're checking for that. And also there might be a corresponding part to the block which is also supposed to be moved, so we're checking for that. If both of them are true, only then we'll move the block, which is what we were doing last time. We were directly moving it right here. Instead now we are keeping track of all the blocks we have to move, because it's possible that there's a block which is related to some other block which is related to some other block, and possibly the last block can move but the rest of them can't. So that was what was causing my issue here. The last block was moving and the rest of them remained where they were, because it remained after that block moved, everything else returned to false. So that's why we're not moving it. And to keep track of it, we're using a set which we are sending all the way from here. Yeah, we're sending it from here. It's a set because it's possible we'll have the same block multiple times and we don't want to move the same block multiple times, so we are keeping a track of it in set so that it's unique. and when we are moving it, we are converting it back to an array so that I can use it like a queue and move the block parts one by one. So that's how this is working, and this is the right way of doing it. I'm wondering if I missed anything else. Yeah, so I did make a small visualizer. I'll add it to this video at the end if I remember to. So this was the visualizer I made to see if everything's working right. Here I've set the interval for each movement to very high so that it's like easier to see, but for my visualization I had actually skipped a lot of steps and I went ahead to the point where I thought issues can occur. So upon increasing the speed, it'll look something like that. So it does it pretty fast, but I started this animation only at the point where I saw issues. So anyway, yeah, so this is how it is. It's quite fun to look at. I think I can set this up as some sort of screensaver or something, like a proper full-size screen. I didn't want to go too like overboard with it. Adding colors itself made it feel a little overboard, but yeah, I thought of adding some emojis or something to represent different things, but yeah, that was going overboard, so I left it at this point, and I quite like this actually. Cool guys, see you on the next one. Bye bye.